Right, welcome everyone to the second video on chapter 20 here, talking about nuclear chemistry. In this video we're going to talk about balancing nuclear reactions and some real life applications of nuclear chemistry. Okay. So, right, to balance a nuclear equation, right, basically what we need to make sure is that the mass numbers on both sides of the equation are equal and the atomic numbers on both sides of the equation are equal, okay? Right? And so that's basically all it is, right? So balancing around normal chemical reaction, right, you need to make sure the number of elements, right, like number of carbon atoms on both sides of your reaction are equal, okay? And in nuclear chemistry, we're not balancing the elements. Instead, we're balancing the protons and neutrons from both sides of our chemical reaction, okay? Right? And so we'll have plenty of examples of this being done in class, right? But again, the main thing here is we want to balance the mass numbers and the atomic numbers, right? So the mass number, right, is like in that lithium 3,7 example, right? The mass number is the 7, right? And the atomic numbers are the 3, right? So basically I need to balance all the superscripts, right? So the superscripts on the left side of my equation have to equal the sum of the superscripts on the right, right? The sum of the subscripts, right? Those atomic numbers on the left side of my equation, right? Has to equal that on my right, okay? And once we balance these things, right, if we have a missing element, right, balancing those equations will help us determine what that missing element is, right? And then once you know the atomic number of that element, right, you can write out what its symbol is by just looking at a periodic table, okay? Right, so nuclear decay is a chemical reaction, right? And every chemical reaction has some type of rate. Well, sort of convenient for us is that nuclear decay is often a first order chemical reaction, okay, right? So that means, right, that it has a first order rate, right? So the rate equals K times concentration of A, right? That means it has a first order integrated rate law that we talked about in the last chapter on kinetics. And that means then that the half-life for this nuclear reaction, any type of nuclear reaction, is given by this equation right here, right, which is essentially 0.693 divided by K, right? Your rate constant. Okay. And the convenient thing for this, right, is that this half-life, right, does not depend on the concentration of A, right? That the half-life is independent of the concentration, it just depends on the rate constant, right? So it doesn't matter what the total amount of stuff you have, right? The half-life is the same every single time, okay? So for example, right, if I'm looking at the nuclear decay of an atom here, right, that has a half-life of 28.8 years, okay? Right, I start off with, say, 10 grams of this substance, right? It's going to take 28.8 years to get to 5 grams. Then it's going to take 28.8 years to get to 2.5 grams. And then it's going to take another 28.8 years to get to 1.25 grams. And then so on and so forth, right? And so, right, it's going to continue to take right, the same amount of time to reduce the amount of that compound you have, that nuclear that radioactive compound that you have, by 1/2 of its current concentration, right? So no matter what the concentration is, it always takes the same amount of time to reduce it by half, right? So if I instead started out at having, say, 6 grams initially, right, it would take, right, if I were to measure the distance between the 6, right here, I have 3 grams, right? If I measure the distance between this, right, this is going to be 28.8 years, okay? Right, so the half-life, right, for, again, a first-order reaction only, half-life rate is independent of what the total concentration is at that point in time, right? And so how do we use this in real-world applications? Well, one of the things we do is carbon dating, okay? So how carbon dating works is, right, right, so there's different isotopes of carbon, okay? Carbon-14 is a radioactive isotope of carbon, okay? And so carbon-14, right, is exists in the world, as well as carbon-13, right, non-radioactive isotopes of carbon, okay? And so as you're consuming food, right, food has carbon in it, right? There's some percentage of that carbon that's carbon-14, okay, right? And so as you're consuming food, you're continually replenishing your body with carbon-14 supply, okay, so that your body contains kind of a consistent percentage of carbon-14 to carbon-13 based off of kind of the percentage of carbon-14 to carbon-13 in the environment, okay? So let's say it's like 10% carbon-14, right? So as you're living, your body has 10% carbon-14, okay? But once you die, you stop eating anything, right? You're dead. You don't eat, right? So your body starts off when you die at 10% carbon-14, and then the carbon-14 slowly continues to decay and decay and decay. So you start off with 10% of carbon-14, but eventually you'll get down to, say, 0% of carbon-14 in your dead body, right, if you wait long enough, right? And so if we measure how much carbon-14 is in some dead sample, some dead thing, and then compare it to the amount of percentage of carbon-14 in some sort of living organism, okay, then you can estimate how much of that carbon-14 has decayed, and that can give you an estimate of the life, like how long ago that thing was alive, right? So if I assume I have 10% carbon-14, right, in my organism when it's alive, based off of, living samples of that organism and things like that, right? So, right, again, 10% carbon-14 in living organisms, right? So I have some dead thing, and then I take a chunk of that dead thing and measure in that chunk what percentage of that carbon is carbon-14 versus carbon-13, right? And let's say it's, 3% carbon-14, right? Well, that means I've decayed from 10% to 3% of carbon-14, and knowing that, and knowing the half-life of carbon-14 will tell me how long it took to get from 10% to 3% carbon-14, okay? And that's how carbon dating works. Okay. Another application of nuclear chemistry is nuclear fission, right? Nuclear fission, right, is the process where a nucleus breaks apart into two smaller nuclei, okay? Right, common form of nuclear fission is uranium fission, right, where a uranium atom, right, collides with a neutron, and that forms two lower lower elements, right, barium and krypton, right, and then 3 neutrons get formed, right. So I need a neutron to start this reaction, and then it creates 3 more neutrons, okay, right. So what can happen if I have a bunch of these uranium atoms together, right? So I have something like this, where if I have, my uranium atoms are these guys here, right? I have my barium, krypton atoms, and then I have my neutrons, right? Are these little black dots, right? Well, what can happen is if I have just one neutron come in and hit a uranium atom, right? It decays, and now it produces 3 new neutrons. Well, if all 3 of those new neutrons hit 3 different uranium atoms, then those will decay, and now I'll produce 9 neutrons, right? So I start off with 1 neutron, 1 radioactive reaction occurring, then I get 3, and then I get 9, and then I'll get 27, and so on and so forth, right? And so this, blows up very quickly, right? And this is how, like, a uranium bomb works, right? Right, a nuclear bomb works in this way. The fact that this reaction can form a chain reaction and sort of catalyze and cause itself to go, right, can end up releasing a large amount of energy in a very short period of time, okay? right? Well, so again, that's if I allow all of these neutrons to find new uraniums, right? Then this thing can really blow up very quickly and cause a very large nuclear decay, right? But if I have, say, a nuclear reactor, okay, so right, these nuclear fission reactions occur in nuclear bombs, but they also occur in nuclear reactors, right, where we use these fission reactions to harness energy, right, to provide electricity to our cities, right? And so how those work, right, is we're trying, instead to having this reaction blow out of proportion, right, we want to control the reaction, right? So there's kind of three levels that you can describe these nuclear reactions at, these chain reactions, right, where you have a subcritical mass. What this means is less than 1 neutron per reaction finds uranium atom, right? So on the previous slide, right, one reaction produces 3 neutrons. So what that's saying is out of those 3 neutrons, on average, less than 1 of them finds a reaction, right? So a number of times, none of those 3 neutrons find a uranium to react with, right? And it's only every once in a while one of those 3 neutrons finds uranium, okay? This will slow down and eventually stop your nuclear reaction, okay? Right? Now, at the critical mass, right, out of those 3 neutrons that are formed, on average, 1 of them finds your uranium atom, and that then can sustain the reaction, right? Because then I have 1 neutron producing 1 neutron that finds another uranium, produces 1 neutron that finds another uranium, and so on and so forth, right? So then I'm releasing the same amount of energy over time, right? Because I'm just having the same number of reactions occur over and over and over and over again, right? And that's your critical mass. That's sort of your stable nuclear reaction, if you will, right? That's going to just continue to produce energy over a long period of time, right? And then we get to the supercritical mass, which is like what happens, right, in a uranium bomb, right, nuclear bomb, okay, where more than 1 neutron finds a uranium atom, right, and this causes then this chain reaction to occur, and this thing increases exponentially, okay, and that's a bad thing, right? And so how a fission reactor works, okay, is it uses the energy from these nuclear reactions to heat up water to generate steam. That steam then just turns some sort of turbine to generate electricity, okay? So all, you know, a nuclear power plant does is, instead of burning coal to heat up water to turn a turbine, okay, through the use of steam, it instead uses the energy from nuclear decay reaction to heat up that water, okay? But same basic concept, right? But what we have in this nuclear reaction are what are called these control rods, okay? Which these control rods absorb neutrons, okay? And so what you do is you lower in those control rods, right? And you try to kind of control, right? You're changing how much the control rods are lowered into your reaction chamber, right, versus not, and that can control, right, how many neutrons in a given chemical reaction are finding uranium atoms, right? Because if they hit the control rods instead of uranium atom, they get used up, right? Those neutrons are gone, right? And so that's how you can control these type of nuclear reactions, right, using these control rods, right? So when things go awry, right, it's because something with the control rods and how these control rods are being introduced into the reaction chamber and things like that breaks down, okay? Somehow the control rods get pulled out, right? These control rods eventually get used up, so you got to replenish them and stuff like that. Maybe they won't replenish, right? So there's a number of things that can potentially cause that to break down, right, and cause a big problem if it does. Okay. And then finally, right, there's nuclear fusion is another type of kind of nuclear reaction, right? This is what the sun does, right? The sun generates its energy, right, through nuclear fusion. So it doesn't do fission, it does fusion, okay? Where it takes lighter elements and combines them into heavier elements, okay? Currently, that's something that we're trying to harness, right? This nuclear fusion, okay? Because it doesn't generate these radioactive elements and have this radioactive waste that we have to deal with for centuries and centuries, okay? Right? And so we ideally want to use nuclear fusion, but the problem is to get nuclear fusion reactions to occur, you have to have it at a very high temperature and a very high pressure situation, right? Like the center of the sun. Okay, so very high pressure because of how massive the sun is, and it's got a lot of energy because of how hot the sun is, right? And so we need, to be able to control that and start that reaction occurring and keep it going is kind of difficult to do. And essentially right now it takes essentially more energy to start these nuclear fusion reactions than you kind of get out of them, right? And so this is still a ways off from being able to harness nuclear fusion as a form of energy. Okay, and so that's it for different examples of nuclear chemistry and how it's used in our everyday lives. Okay, and that wraps up this video on nuclear chemistry.